Hello again. I just wanted to give you a couple of examples. So we want to examine the graphs of two functions. In these two examples, in terms of the concavity, intervals of concave up, concave down, and inflection points. So the first one is a cubic function, the second one is a quartic function. So I'm going to take the derivative first. So we're going to go f prime of x equals 3x squared minus 6x plus 4. The original function is x cubed minus 3x squared plus 4x minus 5. And for the concavity, as I said, we need to find the second derivative. So 6x minus 6. In the next step, if you recall, we used to set the second derivative equal to 0, and that's what I'm going to do. So we end up with x equals 1 clearly. Now, x equals 1, I'm not going to quickly jump on to conclusions saying that it's the inflection point. As I said in the past lecture, we have to wait to see if the second derivative will be changing its sign or not. So in order to figure this out, we're going to construct a chart quickly. So we have x, the domain of a cubic function is a set of real numbers clearly, and we have only 1 point. So one candidate for the inflection point. The second derivative was 6x minus 6, which is 0 at 1. To the right, it's positive. To the left, it's negative because 6x minus 6 has a positive value if x is larger than 1. And it has a negative value if x is less than 1. So what we can say about the second derivative is that it's positive if x is more than 1, and it's negative if x is less than 1. And what we can say about the function y itself is that the function has to be concave down, CD compact disk. Just a joke. Compact, it's not compact disk, it's like concave down. And the other part is CU tomorrow. I mean CU standing for concave up. So the graph is concave up on the right hand side of 1, and it's concave down on the left hand side of 1. So that tells us that this point with x equal to 1 was indeed an inflection point. So if we substitute 1 for x in the equation, we will even find the y coordinate of the inflection point as 1 comma negative 3. So if you just draw a quick sketch of this function whose y-intercept, I can tell it's negative 5. So this is the y-intercept of negative 5. The graph is always increasing, and you can use graphing software for now to draw a sketch. 1 negative 3 would be somewhere here. So the graph goes like this. It's increasing. And then we have our inflection point at 1 comma negative 3. After that, the graph is actually increasing. What is the x coordinate? We can use a software to find out what it is. I think I found it earlier, 2.213. So it's crossing the x-axis at 2.213. So it goes like this. And as you clearly see, at this point, 1 comma negative 3, the graph changes its concavity. So the graph is the graph has an inflection point, and the coordinates of the inflection point is 1 comma negative 3, and it only has one inflection point. Intervals are concave up. I would say it's concave up before. No, it was concave down before the inflection point and concave up after. So for concave up, I would look at the chart wherever the second derivative is positive. I would write that in interval notation. That would be interval of concave up, and it's concave down over the interval of negative infinity up to 1. So everything is actually answered for this question, and you can use Desmos or any graphing software to draw the graph of this cubic function. Later on, we're going to be doing curve sketching, but I want to go step by step. This was an example done for a cubic function. It did have one inflection point. Now I'm going to try this other one, which is a quartic function. For this one, I'm going to take the derivative again. So 4x cubed minus 12x squared, 12x minus 4. The second derivative is 12x squared minus 24x plus 12. If you set it equal to 0, you see that 12 is a common factor. You factor 12 out, and you may notice that this expression here is a perfect square. Actually, it's x minus 1 all squared equals 0, and we know that y double prime will be 0 at x equals 1. So if you solve this equation, you end up with x equals 1. Just like I got x equals 1 before in the past exercise, but at that point, I didn't know if it's an inflection point. Later on, I figured out it was. Now here, again, I don't know, but later on, I will figure out if it is or it is not an inflection point. So for this purpose, I'm going to construct my chart again. So I'm going to set it up like always. And here I should put 12 times x minus 1 squared, and then second derivative, and then the y. So subdividing the chart as always, at x equals 1, we know that second derivative is equal to 0. But then look carefully at this situation, see what happened. I picked this example on purpose. To the right of 1 or to the left of 1, it doesn't matter if you plug in 2, 3, 4, or you plug in like 1/2, 0, -2. Whatever you plug in here in the equation of the second derivative, because it has an exponent of 2, it's going to be always positive no matter what you say, what you do. So the answer here is positive sign before and after 1. And that means that the second derivative, despite the fact that it is 0 at x equals 1, but it doesn't clearly change its sign. It was positive before, it's positive after. So basically the graph was concave up before, and it's still concave up after. So this means that I cannot, I repeat, not count this point as an inflection point. So x equals 1 is not an inflection point. So when it says, what is the inflection point? I'm going to say, hey, you know what? There is no inflection point. So I'm going to say no inflection point. And it's not my fault. That's the way it did happen. Now, is the graph concave up, concave down? If you draw the graph, it's going to look like something like this. If the y-intercept is 1, it's going to look like something like this. It would be very flat. Some graph that looks like a parabola, but it's not a parabola. But at the bottom part, the vertex is very flat, and it's going up like that. So this is how the graph is going to look. And that point at the bottom, which is a minimum point, it is not an inflection point because clearly the graph is concave up before and concave up after. It didn't change its sign. It didn't change its. The second derivative didn't change its sign. The graph didn't change its concavity. So how can I call this an inflection point? It is not. So for the interval of concave up, I would say, you know what? This graph is concave up, all over the place. So I would say it's concave up from -infinity up to 1, and then even from 1 to positive infinity, it is concave up. And I know you're asking, what about 1 itself? And you might have noticed that I excluded 1. Well, think about it. At 1, y double prime is never positive, right? So I can't say it's concave up. It's 0. It's not positive. So for this one, concave down, I would say there is no interval. So I would say there is no interval where the graph is concave down, and there is no interval that you have to mention there. So again, we answered all the questions. Now, just out of curiosity, the name of this point is undulation point. It's not in your textbook. It's not in many textbooks, but just out of curiosity, undulation point is normally a point where the graph does not change its concavity. It's a point where the second derivative is 0, but it doesn't change its sign. A point of undulation, sometimes known as a hyperflex, point, and sometimes known as Meplot point in French. You don't need to know about these details, but I think these two examples clarify, things much better. Another thing I forgot, just for a change. Do you think it's positive thing to be happy? I bet you say yes. So whenever the second derivative is positive, the graph is concave up, like the happy face here, like the smiling here. And then it's a negative thing to be sad, of course. So y double prime is negative, right? And the graph is concave down, all right? So just a brief joke to bring some smile on your face on these special days. And we will continue our lectures soon, okay? You take